Okay, let's go over this. So if you look at the top reaction, trying to figure out the product, the reason why I pointed out the functional groups is because it's not a bad idea to learn the reactions according to the functional group, right? Because really, draw out the mechanism, the only atoms that are going to be interacting are going to be the carbonyl carbon of the ketone, carbonyl oxygen of the ketone, and then the oxygen and hydrogen of each alcohol group, right? So those are the only 4 or 6 atoms, depending upon how you look at it, that are going to be reacting or undergoing any change in this reaction, right? All of the other atoms are going to stay exactly the same, right? So this oxygen is always going to be attached to that carbon. This oxygen is always going to be attached to that carbon, right? This 5-membered ring is always going to be fused, this 5-membered ring at the exact same positions, right? Nothing else is changing. And so if you can identify that 2 alcohols and a ketone under acidic catalysis, acid catalysis, give us a ketal, you should be able to predict what the product is. Right, so if we want to orient ourselves, try to figure out which carbons of the starting material are the product, probably the easiest way to do that is to look at the alcohol, right, and realize that there are 3 carbons in between the alcohol, each have a methyl group, right, and the 3 carbons on the ketal and the product, each with a methyl group, are going to be those on the alcohol, right? So you can see carbon 1 is attached to an oxygen. Here, carbon 1 is attached to the same exact oxygen, right? Carbon 3 is attached to an oxygen. Here, carbon 3 is attached to the same exact oxygen, right? The byproduct of this reaction is going to be water, right? The oxygen of the water comes from the oxygen of the carbonyl. In all of these ketal acetal formation reactions, that's always going to be the same, right? The oxygen of the water develops from the oxygen of the carbonyl. Right? The oxygens attached as part of the ketal are going to be the alcohol oxygens of the starting material. Questions about this?
So the formation of a ketal always has water as a byproduct?
Always is going to have water as a byproduct, yeah.
So does that kind of drive it like towards the equilibrium to like the right a little bit more? Like for instance, like the water weren't there, you said like the entropy would become positive?
No, this is different, right? So this is a substitution reaction, right? We are starting 2 starting materials, ending with 2 products, right? The role of the water in the equilibrium comes more in Le Chatelier's principle, right? So in lab, we did a ketal formation, but we set it up in an apparatus that got rid of the water, right? So if we're getting rid of a reactant that's going to take us back in the other direction, right, that's going to force the reaction towards the products. Okay. There are several ways to get rid of the water. We used a Dean-Stark trap. You could throw in a drying reagent into your reaction so that the drying reagent sucks up that water. But yeah, so that's how we would carry out this reaction. The other way that we can do it, right, rather than removing water, if our alcohol is not, super expensive, super exotic, say we're using ethanol as our alcohol, right, just put in a bunch of ethanol, and that way we have a lot of the reactant, and we can only make a little bit of water relative to that reactant. Yeah.
So you said to look at like the formation of like how the functional groups are. So does that mean if we see like 2 alcohols and a ketone, we can kind of assume that it will form ketone?
2 alcohol groups and a ketone, yeah, under acidic conditions. And that the acidic conditions are kind of important because it can't happen under basic or neutral conditions. So, other questions? Okay, again, as you can see, right, it's easy to get lost in the overall structure, but if you focus on the functional groups, how they interact, right? The rest of the structure is going to stay the same. So the 5-membered rings are still in place. The only thing that's different is the attachment to the carbon, right? The oxygen is obviously gone to water, right? The alcohols have lost hydrogen, but the carbon structure of the diol that we're starting with is still in place, right? Nothing happens to those carbons. We're just showing it in a different conformation. Yeah. Okay. So then the question becomes, how do we get from that product back to our starting materials? All right, the mechanism is going to be relatively easy because we're going to use the same exact intermediates as we did in the forward reaction. All right, so I'm going to abbreviate this a little bit, just so it's a little easier to draw. Right, I'm going to abbreviate it like that. So I'm going to leave out the other 5-membered ring because we know already nothing's going to happen to it, right? It's there in the beginning, doesn't react, it's still going to be there at the end, right? Same with the 3 methyl groups, right? They're there at the beginning, nothing's happening to them, they're there at the end. So just in the interest of time, right, drawing a smaller structure, we'll abbreviate that structure. Right, and we're treating this with acid and water. Okay, so the acid is going to protonate the oxygen of the ketal. Right, so let me actually draw something out really quickly so everybody can follow along before we can move forward with this mechanism. So it's just an even smaller reaction. Okay, so we're starting with the ketal, we're ending with the ketone. Okay, you can see the 2 carbons that were attached to the oxygen in the ketal, right? That becomes the carbonyl oxygen. So if it's bonded to 2 oxygens in the beginning, it's going to have 2 bonds to oxygen in the end. Okay, so that's a really easy way to figure out which carbon was the carbonyl carbon, or for hydrolyzing, which carbon will become the carbonyl carbon. Right, the oxygen here you can see is blue, right? I drew the water oxygen in blue, and it's the oxygen on the carbonyl in the end, right, in the product that becomes blue. So what we're trying to do is replace these 2 oxygens, right, with the oxygen of water. At the same time, the protons that are on the 2 alcohol groups after the reaction is done essentially come from water. So the protons that are on water, we're trying to shuttle to those 2 oxygens in the ketal so they can leave as an alcohol. All right, questions about this? Okay. All right, so the first thing, so whenever these 2 protons from water end up on the alcohols, it's kind of we get the ball rolling with acid, right? And that's why we need an acid to catalyze this reaction, right? To keep things protonated so they act as good leaving groups. So we protonated the oxygen one of the oxygens that's going to become an alcohol. The next step is going to be to push that alcohol group off. So we'll use this other oxygen of the ketal, form a pi bond, and kick the alcohol group off. So this was the oxygen that was attached to the 5-membered ring, right? Still part of the whole molecule because it was, it was breaking up in a ring. Okay? But now hopefully you can see how we're going to start replacing the oxygens that were attached here with the oxygen from water. Now our water can come in. Add to that carbonyl carbon. And we get to this intermediate. You guys a second to catch up. Okay, so when you're doing mechanisms, it's not a bad idea to every once in a while stop, look at your intermediates, and take stock of what you need to do, right, and what you've already done. Okay, so think about where you're going and what electrons need to move in order to get you there. Right, so if you look at this intermediate that we've formed in the mechanism, right, what has to happen in order to get to the product? Anna?
The carbon, the oxygen was single bond, it's gonna break.
Here.
The one below the positive.
This one. That's actually, so this is the oxygen that we just added. So we don't want that to break.
So it'll be the other one.
Yes, good. So this carbon-oxygen bond needs to break.
You have to do a proton transfer from the water that you just added to the substitution.
Awesome, right? So we're going to kick this oxygen out as an alcohol. So we need to transfer a proton from the oxygen that we just added, right? That's going to become the carbonyl to the oxygen that we want to kick out as the alcohol. Yeah.
And then would you carry your non-negative charged OSO3H over to accept the proton at the end?
Yeah, so we can do that. We'll talk about that in a second. Yeah, but we'll need something to carry that proton over, right? And so that's a good question, right? So we need to get a proton from this oxygen over to that oxygen, right? Rachel suggested that maybe we could use the conjugate base of the acid, right? I think in this case, a water is going to be a better molecule. Both are possible, right? I mean, both are going to be basic molecules. The reason why I choose water is because when you do this, you're going to throw in a buttload of water, right? Maybe have a little bit of acid in there to help the reaction. The acid in this is really just a catalyst. And so water is, first of all, going to be probably a little probably more basic than the oxygen of the sulfonate anion, right? But it's also going to be more abundant. So chances of running into a water molecule are going to be much higher than the chances of running into the sulfonate anion. Right? So when you choose a base to do a proton transfer, you want to choose a base, first of all, that's basic, that's reasonably basic, but also figure out which base is the most abundant. If you have a catalyst in there, something in really, really tiny amounts, it might be a good base, but the chances of running into one of those catalyst molecules is going to be really small. Right? But if you have a solvent in there that's basic, like water, then the chances of running into that water much, much greater. Okay? So in this case, we'll use just a molecule of water to shuttle a proton from one oxygen and then we're going to, in the next step, put it on the oxygen that we want to leave.
Wait, what's that step you drew, like, just before?
Here.
Yeah.
So pulling a proton off of the, so we protonated water, right? That's going to show up as H3O plus, so I'll just redraw it in a different way. Right, so it's going to, so we're taking the proton from here, right? And we want to put it on here. So that water was protonated to hydronium, so we're just plucking that proton off of the hydronium,
Okay.
and now it's. Okay, now to get rid of that alcohol, we're going to do the same step that you've seen before, right? Where we have a leaving group that we want to push out of that position. We'll use one of the pair of electrons on one of the oxygens, right? Push out the oxygen that becomes the alcohol. Right, so we're almost at the end. What do we have to do to get to the end?
Use the conjugate base from the beginning to take the H off so that you replace your catalyst.
Okay, so we can use this to take the proton off. What's a better option than the conjugate base?
Water would be more readily available.
Good, right? So as long as water is in the reaction, water is going to be the more readily available base. Right, questions about that? Yeah.
So is it not necessary then for us to make sure that the catalyst is reformed or is that over the
That,
arrow?
it's not really gonna happen in the reaction. We just need to show that an acid is being reformed, right? So whether that acid was the, I mean, you know, the proton initially came from here, that proton will go back to water, right? And even here, right, when we set up this reaction, if we're mixing sulfuric acid, water, and this molecule, these two are gonna react really quickly, and we'll make H3O plus, HSO4 minus, right? So technically, we can even show H3O plus as the acid in the beginning.
Is that why like the catalyst could be a limiting reagent?
The catalyst cannot be eliminated.
So then, if it's not being reformed, then how does it get reused later?
It is being reformed. So I mean, the catalyst essentially is a proton, H plus, right? That proton is you know on this molecule in the beginning, and when the reaction is done, the proton is on that molecule. But the proton is not, or the catalyst is not the full molecule. The catalyst is the acid part of the molecule, right? So we're reforming the acid, right? And we can show this taking that proton up as well. Right? But like I said before, this is a much more probable base and it's also a stronger base.
Is there a way for us to tell like which one is stronger if it's not H2SO4 that's being used as the catalyst?
So yeah, so we just went over the whole acid-base chapter, right? We talked about base strength. So if if these are on your pKa table, you could look at the pKa table. If they have similar structures to the things, you'll use that. Other questions?
Is there a reason why your arrows are both facing the same way?
Just a mistake. It's not 9 o'clock yet, probably.
Is the reverse reaction always going to be like longer than the reverse mechanism going to be longer than the forward? No.
So they should be the same exact number of steps.
Okay.
Right, right? The same intermediates that you see in the forward reaction are the same exact intermediates you would draw in the reverse reaction, right? You're just drawing different arrows to show how you get from intermediate to intermediate. And
Is that always the case, or are there shortcuts sometimes when you're like this?
sorry, no shortcuts. Other questions? So one thing I do want to say, right, when you're deciding, or when you look at this reaction, when you look at this mechanism, right, most of the steps in this mechanism are just acid-base, right, transferring a proton from one thing to another. Okay, so this mechanism is going to be 1, 2, 3, 4, 5, 6, 7 steps, right? Same exact number of steps as the forward acetal ketal formation mechanism, right? Step 1 is an acid-base mechanism. Step 2 and 3, so this is elimination, this is addition. Step 4 is acid-base, right? Step 5 is acid, step 5 is acid-base. Right? Step 6 is an elimination, and step 7 is acid-base, right? So 4 of these 7 steps are just transferring a proton from one thing to another. Right? The other steps, the other 3 steps, that's kind of the meat of the mechanism, getting the oxygens on, getting the old oxygens. Right? But if you look at what we have to do, you can hopefully see why there are so many acid-base steps, why there's so many proton transfer steps, right? Because these 2 protons here have to get to those 2 oxygens, right? We can't do that intramolecularly, so we're going to need a shuttle to help us do that, right? So that's going to necessarily add more steps, more acid-base steps. Questions? Right, so next functional group that we're going to talk about is our imines and enamines. Right, and these are going to be developed when we add nitrogen nucleophiles to aldehydes and ketones. So let me give you a little scheme here. Right, so the first reaction is going to be imine formation. Again, just like with acetals and ketals, this can happen to aldehydes as well as ketones. Right? We're not going to differentiate between imines from ketones and imines from aldehydes. They're called the same thing. Right? So just know that this reaction can happen on both. And it's going to happen between a ketone and an aldehyde, and specifically a primary amine. Right? So an amine with 2 hydrogens on it. second reaction, functionally, it more or less looks the same, right? Mechanistically, it more or less looks the same. Okay, again, we're starting with an aldehyde or a ketone, right? So in this reaction, I'm just showing an aldehyde, but the same reaction occurs with a ketone, right? But I'm treating that aldehyde or that carbonyl with a secondary amine, right, rather than a primary amine. So this is the difference between the two reactions, right? One is a primary, and one is reacting with the secondary amine, right? The primary amine, when it reacts with a ketone or aldehyde, is going to make an imine, right? The secondary amine, when it reacts with a ketone or an aldehyde, it's going to create a functional group called an imine.
So the number of hydrogen determines if it's primary or secondary amine?
Yes, the number of hydrogens attached to the nitrogen. Sure.
We're gonna have no acid catalyst for this, right?
Yeah, there is an acid catalyst. Thank you. Other questions? Okay, so knowing how carbonyl groups function, right? They function mostly as electrophiles. See if you can figure out the mechanism for the imine formation. All right? Just like in the acetal ketal, the two hydrogens of the nitrogen end up on the oxygen in the product of water, right? And the oxygen in the water comes from the oxygen of the carbonyl, right? So that is obviously getting replaced by the nitrogen of the amine, the starting material, right? See what you can draw up. All right, I'll even draw step one for you. All right, so this is going to be the first step of the mechanism.
For the imine first.
can't talk to each other, it's not an exam, each other out. Remember your principles of drawing mechanisms, right? Arrows always have to start a pair of electrons, go to an atom that's accepting those electrons. Yeah.
Show the two hydrogens, because I know you still have to have all this somewhere. I just need them. You put one on the oxygen. No. Like, oh, okay. I mean, you did. I missed it. No, I just gotta do that. Yeah. I don't know how oxygen. Yeah, that's kind of. I wasn't sure if that was something we could do. I think so. That's what I was thinking. So it's going to be able to go into the orbital integrally. Yeah. So. The fact that they're single bonds isn't good.
You would still have S. Like you would just have this one.
What?
Okay, let's go over this really quickly. Okay, so we added our amino group. First of all, amines are nucleophilic, much more nucleophilic than alcohols, right? The nitrogen is less electronegative. Its electrons that it has, its lone pair, are a lot more promiscuous than the ones on oxygen. So it's okay adding to a carbonyl without that carbonyl first being protonated, right? This is a pretty good nucleophile electrophile match, right? Once we make our first intermediate though, if we have acid hanging around, say in the form of sulfuric acid, right, then that negatively charged oxygen that we just generated will get protonated. Okay, in order to lose that oxygen as water, right, which happens in both of these reactions, we need to add another proton on there. Okay, you can see that we have one next door, right? This is the acidic form of an amine, an ammonium compound. But we would need something to take the proton off of here, right, and deliver it to that oxygen. Okay, walking around, a couple of people suggested that we use water, but, and this is something that the trap that people fall into every year, right? We use water once on the board when we're going over a mechanism, and then you think, oh, I can use water anytime I want to transfer a proton. There's no water in this reaction, right? So we can't propose a base that's not available in the reaction, right? We didn't put it in the reaction. But we have an amine, right? There's an amine in the reaction that can be basic. We have this oxygen atom that has some basic properties, right? So we have things that if we want to transfer a proton, we can do that, right? We're just transferring, we're not creating some product favored acid base equilibrium. So I'm gonna just suggest we use the amine. Pluck a proton off that nitrogen. Right, and then with the conjugate acid of the amine that we just added, we could deliver that proton to the oxygen. Right, and that creates our water leaving group, just like we created in the acetal formation reaction. Okay, to get that water leaving group to leave, it doesn't just take off by itself, but just like in the acetal ketal reaction, we're going to use the next door heteroatom, form a pi bond, and push that water out. Right? The intermediate that we're creating is called the iminium intermediate. All right, and that IUM suffix we have on that word, just like ammonium, right? Iminium, that IUM indicates a positively charged nitrogen. Right, and then the last thing that we have to do, we have to reform our acid catalyst. Right, we'll just use a base that's abundant and powerful, and we'll use the amine, pluck that proton off at the end. And that gets us to our amine. Questions about this mechanism? Okay, so just like with acetals and ketals, imines can be hydrolyzed, right, back to their carbonyl and amine components. Right. So so these reactions are in equilibrium. If we take an imine, add water, and an acid catalyst, we'll go back the other direction, right? If we take an enamine, add water, and an acid catalyst, we'll go back the other direction. So what I want you to do this weekend is, first of all, see if you can draw a forward mechanism for this reaction, right? So this is, again, the secondary amine with an aldehyde or a ketone, right? Creates an enamine. Look why, I mean, you can see why it's hopefully called an enamine, right? We have an alkene next to an amine group. Pick your friends, you can't pick your enamines. So draw the mechanism for this reaction, and then see if you could draw the two hydrolysis mechanisms, right? The backward mechanisms for the imine to the ketone and the ketone to the.
I have a question.
Yeah.
How come you use sulfuric acid? It's not supposed to be in the reaction.
I just had acid catalyst in there.